You are holding a rock. It is black, smooth, and sharper than anything else you have ever touched. You did not make it. You found it near a volcano, wedged into a ridge of cooled gray stone, and when you cracked it with another rock, it broke into a curved edge so thin it could slice skin without you feeling it. This is obsidian. Volcanic glass, and roughly 7,000 years ago, at a site called Karinduzi in the Rift Valley of Kenya, a human ancestor, Homo erectus, picked up a piece of this same material and used it as a tool. That is the first known moment a human held glass, not a window, not a drinking cup, not a lens, a rock that happened to form when lava cooled too fast for crystals to arrange themselves. Glass existed on this planet for billions of years before anyone figured out how to make it. Lightning struck sand and left behind hollow tubes of fused silica called fulgurites. Meteorite impacts melted entire desert floors into sheets of pale yellow crystal. Volcanoes poured out rivers of molten rock that cooled into obsidian fields. Glass was everywhere. Nature had been making it since before life existed. And for hundreds of thousands of years, humans used it without once understanding what it was or that they could create it themselves. That moment, the moment someone figured out how to make glass from scratch, changed the world more than almost any other invention in human history. And it probably started with an accident nobody noticed. So how did we get from a volcanic rock to the screen you are looking at right now? The answer covers 5,000 years, a dozen civilizations, at least 3 accidental discoveries, and a physics problem so strange that scientists are still arguing about it. Let us start with what glass actually is, because most people get it wrong. Glass is not a liquid. You may have heard the old claim that glass is a liquid that flows very slowly, and that the windows in old cathedrals are thicker at the bottom because the glass has been slowly oozing downward for centuries. This is a myth. Physicist Edgar Dutra Zanotto at the Federal University of São Carlos in Brazil published a paper in 1998 in the American Journal of Physics. He calculated that cathedral window glass would take longer than the age of the universe, more than 13.8 billion years, to show any measurable flow at room temperature. The uneven thickness of old cathedral windows is because of how they were manufactured. Medieval glassmakers spun molten glass into flat discs, and the discs were naturally thicker on one edge. Glaziers just installed the heavy side at the bottom. The glass did not move. It was made that way. What glass actually is something genuinely weird. It is an amorphous solid. That means its atoms are arranged in a disordered pattern, like a liquid frozen in place, but it has the rigidity of a solid. It never formed a crystal structure. It skipped that step entirely. When you cool most liquids slowly, the atoms line up into neat, repeating grids, crystals. That is what happens with ice, with salt, with metals. But if you cool certain liquids fast enough, the atoms never get the chance to organize. They just stop moving while they are still in a chaotic arrangement. That is glass, a material caught halfway between 2 states of matter. Permanently stuck in a moment of transition, physicists still do not fully agree on how to classify it. And that ambiguity, that strange in-between quality, is part of what makes glass so useful. It can be transparent, it can be shaped, it can be colored, it can be made thinner than a human hair or thicker than a bank vault wall, and it all starts with sand. The main ingredient in most glass is silicon dioxide, SiO2, which is the primary component of common sand. Pure silica melts at roughly 1713 degrees Celsius. That is far too hot for any ancient furnace. But add a flux, a material that lowers the melting point, and the temperature drops to something manageable. The flux that ancient glassmakers used was natron, a naturally occurring mineral made mostly of sodium carbonate found in dried lake beds in places like Wadi Natron in Egypt. Mix sand with natron, heat it to roughly 1,000 to 1,100 degrees Celsius, and the silica melts. But there is a catch. Glass made from just sand and natron is water soluble. It dissolves in rain. To fix that, you add a stabilizer, usually lime, calcium oxide from crushed limestone or seashells. The standard ancient glass recipe was roughly 70% silica, 15% soda, and 10% lime. That formula, give or take a few percentage points, is essentially the same recipe used in most of the glass produced on Earth today. A 5,000-year-old recipe that still works. Now, here's the question that matters. Who figured this out first? And how? The Roman historian Pliny the Elder, writing in the 1st century AD, told a story that has been repeated for 2,000 years. Phoenician merchants, camping on a beach near the river Belus in what is now Israel, rested their cooking pots on blocks of natron they were transporting as cargo. The heat of the fire combined the natron with the beach sand, and a stream of molten glass flowed out from under the pots. It is a wonderful story. It is also almost certainly not true. An open beach fire reaches maybe 600 to 800 degrees Celsius, even with natron lowering the melting point. That is nowhere near hot enough to produce glass. The story told by Pliny is a foundation myth, not a scientific account. The real origins are messier, less romantic, and much older. The earliest man-made glass objects are small beads found in Mesopotamia and Egypt, dating to roughly 2500 to 2300 BC. That is over 4,500 years ago. The most widely accepted theory is that glass was discovered accidentally during the production of faience, a quartz-based decorative material coated with a glassy glaze that was popular across the ancient Near East. When silica-rich materials mixed with alkali flux in a hot kiln, the surface sometimes vitrified, producing a thin layer of actual glass. At some point, someone noticed that this glassy material could be scraped off and produced as a standalone substance. Another theory, proposed by A. Leo Oppenheim in his landmark 1970 study Glass and Glassmaking in Ancient Mesopotamia, suggests that the glassy slag from copper smelting may have provided the initial inspiration. Either way, the discovery was almost certainly accidental. Nobody set out to invent glass. They were trying to make something else and got glass as a byproduct. Which, when you think about it, is how a surprising number of the most important inventions in history actually happened. And here is something most people do not know. Egypt and Mesopotamia appear to have developed glass production independently. Andrew Shortland, an archaeologist at Cranfield University, published a study in 2012 using laser ablation mass spectrometry to analyze the chemical signatures of early glass from both regions. The Egyptian glass had distinct trace element profiles consistent with Egyptian raw materials. The Mesopotamian glass had different signatures. Two civilizations, working with the same basic chemistry, arrived at the same invention separately. But here is the thing that connects this story back to why glass matters. For the first 1,000 years of its existence, glass was not a common material. It was a luxury, a serious luxury. During the Late Bronze Age, roughly 1550 to 1200 BC, glass was valued alongside lapis lazuli, turquoise, and gold. The diplomatic correspondence found at Tel el Amarna, letters exchanged between Egyptian pharaohs and other Near Eastern rulers around 1350 BC, includes complaints about the quality of glass sent as diplomatic gifts. One ruler writes to the pharaoh essentially saying, "The glass you sent me was terrible. They were treating glass the way modern heads of state treat gemstones, because at that point in history, glass was that rare." The most important ancient glass workshop ever discovered was found at Amarna itself, the short-lived capital built by Pharaoh Akhenaten around 1350 BC. W.M. Flinders Petrie first excavated the site in 1891 and found glass rods, canes, ingots in multiple colors, partially finished vessels, and the remains of furnaces. More recent excavations by Paul Nicholson of Cardiff University, conducted between 2004 and 2007, clarified that the glassmakers at Amarna used a two-stage process. First, raw materials were partially melted into a rough mixture called frit. Then the frit was crushed and remelted at higher temperatures to produce clear, bubble-free glass. That is not a simple operation. That is industrial chemistry, performed 3,400 years ago. And there is one piece of ancient glass that connects this entire story to something far older than any human civilization. In 1922, Howard Carter opened the tomb of Tutankhamun and found a carved scarab beetle set into a ceremonial pictorial breastplate. For decades, the scarab was identified as chalcedony, a common gemstone. It was not until 1998 that Italian mineralogist Vincenzo de Michele of the Museum of Natural History in Milan examined the scarab using infrared spectroscopy and confirmed that it was actually Libyan desert glass. A pale yellow-green natural glass, nearly 98% pure silica, found scattered across the Great Sand Sea on the border of Libya and Egypt. It formed roughly 29 million years ago, almost certainly from a meteorite impact or a cosmic airburst that generated temperatures exceeding 1700 degrees Celsius, melting the desert sand into glass. Egyptian craftsmen found a piece of 29 million year old glass in the desert, recognized its beauty, carved it into a sacred scarab, and placed it on the chest of a dead king. They were working with glass formed by a cosmic event that happened millions of years before any human existed, and they did not have the faintest idea what it actually was. They just thought it was beautiful. Now, the earliest glass vessels were not blown. They were made using a technique called core forming, which appeared around 1500 BC. A craftsman shaped a core of clay and dung around a metal rod, then dipped it into molten glass or wound hot glass trails around it, smoothed the surface on a flat stone called a marver, and scraped out the core after cooling. The result was a small, colorful bottle, typically 6 to 20 centimeters tall, used for perfumes and cosmetic oils. Each one took hours to make. They were beautiful, they were expensive, and for over 1500 years, this was the only way to make a hollow glass object. Think about how limiting that was. For 15 centuries, every glass vessel on Earth was made by the same painstaking one-at-a-time process. Glass remained a luxury because nobody had found a faster way to shape it. And then, sometime around 50 BC, on the coast of what is now Lebanon or Syria, someone had an idea that changed everything. They put a blob of molten glass on the end of a hollow iron pipe, and they blew. The invention of glassblowing is one of the most transformative technological leaps in human history, and almost nobody talks about it. Before glassblowing, making a single glass vessel took hours of skilled labor. After glassblowing, a trained craftsman could produce one in minutes. Dozens in a day. The technique made glass vessels thinner, lighter, larger, and for the first time, genuinely transparent. And because it was so much faster, glass went from a luxury material affordable only to the elite to an everyday commodity that ordinary people could own. The earliest blown glass vessels have been found in Jerusalem, dating to the mid-1st century BC. E. Marianne Stern, one of the leading scholars of ancient glass, published an analysis in 1999 arguing that the technique likely developed among workers who were already familiar with blowing through tubes for metalworking bellows. Someone took that same motion, applied it to molten glass, and accidentally invented mass production. One of the earliest named glassmakers in history is a man called Ennion, a Sidonian from what is now Lebanon, active in the 1st century AD. Ennion produced mold-blown vessels and signed them with his name in Greek. Ennion made this. His signed cups and bottles have been found across the entire Mediterranean, from Israel to Italy. The Metropolitan Museum of Art in New York holds one of his pieces. Ennion was not just a craftsman. He was a brand, one of the first brand identities in the history of manufacturing, stamped onto a glass cup 2,000 years ago. The Romans did not invent glass blowing, but they industrialized it the way they industrialized everything, within decades. Roman glass workshops were operating from Cologne to Alexandria, mass-producing standardized bottles, cups, bowls, and storage jars. The Roman writer Strabo, writing around 20 AD, noted that glass-drinking vessels could be purchased for a copper coin. Glass had gone from rivaling gemstones to costing less than a meal. And the Romans used glass for something nobody had tried before: windows. Evidence of Roman window glass has been found at Pompeii, preserved under volcanic ash from 79 AD. Small, thick, not fully transparent, but they admitted light while keeping out the weather. The idea that you could see through a wall is so basic to us now that we forget someone had to invent it. The Romans did. But the Romans also produced glass objects so technically demanding that modern craftsmen struggle to replicate them. The Lycurgus Cup, now in the British Museum, is a 4th century Roman cage cup that does something no other surviving ancient glass object does. It changes color. When you light it from the front, it appears opaque jade green. When you light it from behind, it turns translucent ruby red. For centuries, nobody could explain how. In 1990, researchers at the British Museum, including Ian Freestone, examined the glass using transmission electron microscopy and found the answer. The glass contains particles of gold and silver, roughly 50 to 100 nanometers in diameter, far too small to see with the naked eye. Those nanoparticles create the color-changing effect through surface plasmon resonance. The same physics that modern researchers are exploring for medical diagnostics and biosensors. The Romans created nanotechnology 1,600 years before anyone named the concept. After Rome fell, the center of glass innovation shifted east. Islamic glassmakers, working between roughly the 7th and 15th centuries in workshops across Syria and Egypt, developed techniques that European glassmakers would not match for centuries. They mastered enameling, gilding, and metallic staining. The mosque lamps produced in Damascus and Aleppo during the Mamluk period, roughly 1250 to 1517, are among the most celebrated objects in Islamic art. And then Timur sacked Damascus in 1400 and reportedly took the glassworkers of the city to Samarkand. The Syrian glass industry, one of the finest in the world, was effectively destroyed. Meanwhile, in Venice, glass was becoming a state secret. On November 8, 1291, the Venetian Republic issued a decree ordering all glass furnaces moved from Venice to the island of Murano, about 1.5 kilometers across the lagoon. The official reason was fire prevention. The real reason was control. Moving every glassmaker to an island made it far easier to guard trade secrets and prevent artisans from leaving. Glassmakers on Murano were given extraordinary privileges. They could carry swords, their daughters could marry into the nobility, but they were forbidden from leaving the Republic. If a glassmaker fled to a foreign country, the state would first attempt to persuade them to return. If that failed, their families could face consequences. Around 1450, a Murano glassmaker named Angelo Barovier developed something the world had never seen. He called it cristallo. Nearly colorless, transparent glass of unprecedented clarity, achieved by carefully purifying his raw materials and using manganese dioxide as a decolorant to neutralize the green tint caused by iron impurities in the sand. Cristallo was a sensation across Europe. It looked like rock crystal, and it cemented the reputation of Venice as the undisputed capital of glassmaking for the next 2 centuries. France wanted those secrets. In 1665, Jean-Baptiste Colbert, finance minister to Louis XIV, successfully lured several Murano glassworkers to Paris. Some of those workers later died under mysterious circumstances, leading to suspicions of Venetian poisoning, but the damage was done. The French established the Manufacture Royale de Glaces de Miroir, which eventually became Saint-Gobain, one of the largest glass companies in the world, still operating today after more than 350 years. And between 1678 and 1684, they installed 357 mirrors in the Hall of Mirrors at the Palace of Versailles, a political statement in glass. France no longer needed Venice. Now, speaking of mirrors, before glass mirrors, people saw their reflections in polished metal, bronze, and silver, which gave dim, distorted images. Venetian glassmakers developed flat glass mirrors using a tin mercury amalgam in the early 16th century, and Venice held a near monopoly on quality mirrors for decades. In 1835, German chemist Justus von Liebig developed the modern silver-backed mirror, replacing toxic mercury with a thin layer of metallic silver deposited through a chemical reaction. That is essentially the same process used in most mirrors today. Every time you look at yourself in a mirror, you are looking at a technology that traces back to the laboratory of a German chemist nearly 2 centuries ago. And while Venice was guarding its glass secrets, glass was quietly doing something far more consequential on the other side of Europe. It was inventing science. Eyeglasses were invented in northern Italy, probably Venice or Florence. Around 1286, a 1306 sermon by the Dominican friar Giordano da Pisa mentions that it is not yet 20 years since there was found the art of making eyeglasses, which make for good vision. Historian Vincent Ilardi, in his 2007 book Renaissance Vision from Spectacles to Telescopes, argued that eyeglasses extended the productive reading life of scholars by 15 to 20 years, effectively doubling the working career of intellectuals. Before spectacles, anyone who developed presbyopia, a near universal condition by age 40 or 50, lost the ability to read fine print. Glass gave aging scholars their eyes back. And when the printing press arrived around 1452 and flooded Europe with books, the demand for vision correction exploded. Glass lenses and the printing press fed each other. More books meant more readers needed glasses. More readers with glasses meant more demand for books. Without glass, the age of mass literacy might have been delayed by centuries. In 1608, Hans Lippershey, a spectacle maker in Middelburg in the Netherlands, filed a patent for the first telescope. The following year, Galileo Galilei built his own improved version, pointed it at Jupiter, and observed 4 moons orbiting the planet. He published his findings in Sidereus Nuncius in March 1610. That single observation, 4 dots moving around a distant point of light seen through 2 curved pieces of glass, overturned the geocentric model of the universe. Everything revolved around Earth until someone looked through glass and proved it did not. And on the other end of the scale, Antony van Leeuwenhoek, a Dutch draper with no formal scientific training, ground tiny, near spherical glass lenses that achieved magnifications of up to 275 times. Using these single-lens microscopes, he became the first person to observe bacteria in 1676 and spermatozoa. In 1677, he called them animalcules, little animals, and described them in letters to the Royal Society in London. All of modern microbiology begins with a self-taught cloth merchant grinding pieces of glass in a workshop in Delft. 2 pieces of shaped glass. One pointed at the sky. One pointed at a drop of water. Between them, they revealed that the universe was infinitely larger and infinitely smaller than anyone had imagined. That is what glass did to human knowledge. It cracked it open. In 1903, a French chemist named Edouard Benedictus accidentally knocked a glass flask off a shelf in his laboratory. The flask hit the floor and cracked, but it did not shatter. The pieces held together. Benedictus realized the flask had contained a solution of cellulose nitrate that had evaporated, leaving a thin, transparent film coating the inside of the glass. That film held the broken pieces in place. He filed a patent for laminated safety glass in 1909. The first major application was gas mask lenses during World War I. Today, every car windshield on Earth uses a descendant of that accidental discovery. In 1952, an engineer named Alistair Pilkington at the Pilkington Brothers Glass Company in St. Helens, Lancashire, conceived an idea that would transform the glass industry completely. Pour a continuous ribbon of molten glass onto a bath of molten tin. Tin melts at 232 degrees Celsius. Glass at that stage is roughly 1100 degrees. Because glass is less dense than liquid tin, it floats, spreading into a perfectly flat sheet under the force of gravity. The glass cools gradually as it moves along the tin bath, emerging as a continuous ribbon of flawless flat glass with a uniform thickness and fire-polished surfaces. The development took 7 years and cost roughly £7 million. Pilkington Brothers announced the float glass process on January 20th, 1959. Today, over 90% of all flat glass in the world is produced using this method. Every window you have looked through today was almost certainly made by floating liquid glass on liquid metal. And then glass went even smaller. In 1966, Charles Quenkau, a Chinese-born British engineer working at Standard Telecommunication Laboratories in Harlow, England, published a paper with his colleague George Hockham that proposed something that sounded absurd. Glass fibers, thin strands of ultra-pure silica, could be used to transmit information using light. The problem was purity. The best glass fibers available at the time lost so much light over distance that they were useless for communication, roughly 1,000 decibels of loss per kilometer. Kao realized that the loss was not a fundamental property of glass. It was caused by impurities. Make the glass pure enough, and light could travel through it for kilometers. In 1970, researchers Robert Maurer, Donald Keck, and Peter Schultz at Corning Glass Works produced the first optical fiber with losses below 20 decibels per kilometer using fused silica doped with titanium that crossed the threshold from useless to revolutionary. Today, over 500 million kilometers of optical fiber have been installed across the planet. More than 95% of all international internet data travels through glass threads thinner than a human hair at the speed of light under the ocean floor. The internet is glass. Charles Kao won the Nobel Prize in Physics in 2009 for making it possible. In 1960, Corning Glass Works developed an experimental chemically strengthened glass called ChemCore as part of a project exploring ultra-strong glass. The glass was strengthened through ion exchange, submerging it in a hot potassium salt bath so that larger potassium ions replaced smaller sodium ions on the surface, creating a layer of compressive stress that made the glass remarkably strong and scratch-resistant. Despite successful tests, ChemCore never found a commercial market. The project was shelved for 45 years. It sat in a filing cabinet. Then in 2006, Steve Jobs approached Corning CEO Wendell Weeks with a problem. Apple was developing the iPhone and needed a strong, scratch-resistant glass for the touchscreen. Weeks told Jobs about the dormant ChemCore project. Jobs was skeptical. Weeks reportedly told him, "Do not tell us what we cannot do." Corning reformulated the glass, rebranded it Gorilla Glass, and delivered it in time for the first iPhone, launched on June 29, 2007. A glass technology developed during the Cold War sat dormant for nearly half a century before ending up in your pocket. By 2024, Gorilla Glass was used in over 8 billion devices worldwide. So, the answer: how did humans invent glass? They did not plan it. Nobody sat down and said, "I am going to melt sand into a transparent solid." Glass was an accident, noticed by someone paying attention during the production of faience or the smelting of copper, roughly 4,500 years ago in Mesopotamia or Egypt. For its first 1,000 years, glass was a luxury material rivaling gemstones, produced in palace workshops under royal patronage. The invention of glass blowing around 50 BC shattered that exclusivity and turned glass into the first mass-produced transparent material in history. From there, glass became windows, mirrors, lenses, telescopes, microscopes, fiber optic cables, and the screen you are holding right now. Was glass a single invention from a single source? Almost certainly not. The chemical analysis by Andrew Shortland confirmed that Egypt and Mesopotamia developed glass independently. The probability that glass was discovered only once and spread from a single origin is low, perhaps 20 to 25%. The more likely scenario, at roughly 75 to 80% probability, is that glass was discovered independently in at least two places, because the same raw materials, the same kilns, and the same high-temperature processes existed in both regions simultaneously. The accident was going to happen. It was just a question of where it happened first. But here is the part that stays with me. Glass is sand. That is all it has ever been. Heated sand. Shaped by human hands. Cooled into something transparent. And from that single material, humans built lenses that revealed the structure of the universe. Fibers that carry the sum of human knowledge under the ocean at the speed of light. Mirrors that let you see your own face. Windows that let you see the world without feeling the weather. A scarab carved from a 29-million-year-old cosmic impact, placed on the chest of a teenage king. You are surrounded by glass right now. You are probably looking through it. And the only reason any of it exists is that someone, thousands of years ago, noticed something strange happening in a kiln, a thin, shiny substance forming where it should not have been, and instead of scraping it away, they looked closer. That is the entire history of glass. Someone looked closer,